All right, so what we're going to look at today is conditional statements. And that is actually something that I had skipped over when I was trying to condense some stuff. And I gave you a brief rundown of a couple of things as we went through some other stuff. But I know I've told you before that I meet with the calculus teachers and pre-cal teachers once a week. And one of the things, the calculus teachers has been to a training last weekend, and they spent a whole long time talking about conditional statements and converses and inverses and all that stuff we're going to talk about today, and the way that they need it and use it in calculus and all that kind of stuff. And I know it's important. That's why everything we do is, well, not everything we do, most of what we do is important. But I didn't, so I felt like especially after that discussion and how much time they spent on it, that I really needed to go back and make sure that you fully understand all the pieces and truth values and things like that. So we're going to go and look at this. It's going to seem a little bit more like an English lesson today, probably. I already forgot again. What page? Thank you. 56. Okay. All right. So we have conditional statements. Those are statements where conditions are put on them. Okay. If you studied for your quiz, then you would do well, right? So if you studied for your quiz, then if that happened, then the second part would happen. So you have two pieces to it. All right. You have a hypothesis and a conclusion. The hypothesis has to be true in order for the conclusion to be true, all right? So we've got a blank blank. So this is a conditional statement. That's what goes in these blanks. A conditional statement is a statement that can be written in the form if P then Q. It says can be written. It doesn't mean it has to be. We can make those statements without them literally having if and then in them. All right. If you fail a class, then you will be grounded, right? I mean, that's a conditional statement that maybe some of you have heard before. But the symbolic form, we've looked at this already. It looks like this, and the way you read that, let me make that arrow better. The way you read that is right here. If P then Q. You can take entire courses on symbolic logic, which all stuff looks like that. All right, took one in college, and the professor was horrible. He sat in a rolly chair and rolled around the front of the room because he was too lazy to even get up. We pretty much taught ourselves, but the whole textbook, pretty much you flip through and it looks like stuff like that. Okay, and it's all about how the pieces work together. So there are times where you need to read a statement and decide whether it's true or false, but then there are times where it's how it is set up that gives that away for you, and that's one of the important things for you to be able to see with this. All right, so then the next part is this, the hypothesis. So the hypothesis, and we've talked about a hypothesis before, like in science, right? And it's not really a prediction here necessarily. It's just the first part of what the sentence. So the structure of these is important. Knowing when you read this, which one is the hypothesis and which one is the conclusion. So the hypothesis is the part P of a conditional following the word if. Okay, so it doesn't include the word if. It follows the word if. And then the conclusion is the part Q of a conditional statement following the word then. Okay? If this, then that. If P, then Q, whatever it may be. Venn diagrams can be used to represent conditional statements. So if I have a Venn diagram, okay, those are not brand new to you, but most of the time the Venn diagrams that you have had have been intersecting circles that might look more, or ovals, whatever they may be, that might look more like this, right? And then these are two things and something that they share. But it can also look like this, like something can live completely inside of something else, right? Yeah, exactly. The different types of numbers, things like that. If we wanted to talk about, if like the outside circle was students at Pasadena Memorial High School, and then this inside circle would be freshmen at Pasadena Memorial High School. So all the freshmen that go to this school are also just students at the school, right? You can live 100% in a different one. So when you have conditional statements like that, it's if this, then that, right? So if P, then Q. What do you think goes on the inside? The P or the Q on the little inside oval? What is the guarantee? Like, let's think about this. If you fail a class, then you will be grounded, right? So are there other reasons you could get grounded? Yes. Okay. But if you fail a class, it's pretty much a guarantee, right? Depending on who your parents are. But that's, that's what I'm saying here. So the P goes in here because this is if you fail a class that lives in the world of all of the things you could get grounded for, right? So when you have a Venn diagram and you're trying to come up with a conditional statement, you read from the inside out. Okay? Does that make sense? So if whatever's on the inside, then whatever's on the outside. Does that make sense to you? Okay. We're all good? So we're going to go through a couple of these real quick. We're going to underline the hypothesis of each conditional and circle the conclusion. So the if part, it has the hypothesis. But remember, it comes after the if. So the hypothesis here is just, the statement says, if a butterfly has a curved black line on its hind wing, then it is a viceroy. So the hypothesis does not include if. It starts here. Bam, that's your hypothesis. Then the conclusion is the viceroy. It doesn't include the then part. Does that make sense? B is an example of when it's not written in if-then form. It still has the word if in it. I mean, we could even write them without the word if. But here in B, what is the hypothesis? The last part. So it is a rational number. That's your hypothesis. Okay? And then a number is an integer is your conclusion. If you live in Pasadena, then you live in Texas. Okay? If an angle is obtuse, then it has a measure of 100 degrees. If I am in pre-AP geometry at PMHS, then Mrs. Finnan is my teacher. Now, are all of these statements true statements? No. Actually, most of them are not. You may not know about the butterfly. It is true. Okay, maybe that was one you know. There you go. You learned something about butterflies today. Maybe you're not even sure about the number thing. But let's look at C. If you live in Pasadena, then you live in Texas. Well, those of you that live in Pasadena, do you live in Texas? Yeah, you totally do, right? But there's a Pasadena in California too, right? So even though it's true for some people and it's true for a large number of people that actually live in Pasadena, right? If you can find even one time when it's not true, that means the statement overall is false. Does that make sense? Because it has to be true all the time. And it's not a true statement, but it's still a statement. Do people make false statements all the time? Heck yeah. It still has a hypothesis and a conclusion. All right. So we're going to look at truth values too, but right now these really doesn't matter. What about this one? If an angle is obtuse, then it has a measure of 100 degrees. It's false. It's a false statement because it's not always true. Does that make sense? So when you think about things as always, sometimes, never, that's a 3-part thing. True and false is just a 2-part thing. So if it's always, it's true. If it's sometimes or never, that makes it false. Okay? Because true means always true. We're just talking true, false. Then if I am in pre-AP geometry at PMHS, then Miss Finnan is my teacher. Well, I'm the only pre-AP geometry teacher. But is this a true statement? Yes. Okay. So that is a true statement. We'll look at why some of these, their truth values change here in just a minute. All right. So let's look at the next page. Here are the different forms of the conditional statements. There are 4 conditionals that are related to each other. The first one, and we're just kind of repeating a little bit of what's on the front. A conditional statement, and I know we already wrote this on the front, but I want it here too, is a statement that can be written in the form if P then Q. So that's what this says, if P then Q. Right. So then we have 3 other ones that relate to the conditional statement. We've already talked about this next one. It is the converse. That's when we just reverse things, right? So a converse is formed by exchanging the hypothesis and the conclusion. So it's if Q, then P. Okay, we've already looked at a couple of those because I skipped over this for a little while. Now, there's a little symbol, and you have more room up at the top than I do, but there's a symbol that we're going to use that looks like this. It's like the squiggly that goes above the equal sign for congruence, which could also mean similarity, but that's not what it means right here. But when you get the squiggly, that right there means not. Okay, so when you want to negate it, like I'm not using a negative sign because we're using words, but that means not in the symbolic world. Okay? Because when we get here, it says the blank is the statement formed by negating be conditional, taking this one and making it negative. So if it's if P then Q, I need it to be if not P, then not Q. So this is called the inverse. So what we would say here is if not P, then not Q, whatever it is. So let's think about this. If you fail a class, then you are grounded. There's your conditional. The converse would be, if you are grounded, then you failed a class. Is that going to be always a true statement? No, because there's probably something else you're going to do to get yourself grounded, right? And then the inverse is making this negative. Remember, this one was, if you fail a class, then you will be grounded. So the negative of that would be, if you do not fail a class, then you will not be grounded. Okay, still, that's the inverse. Would that always be true? Probably not. I mean, it depends, I guess. But all right, so then the last one is the contrapositive. Okay, so the contrapositive is the statement formed by negating the converse. So the conditional is the original. The converse, you just switch the two. The inverse, you make them negative. The contrapositive, you do both. You switch them and make them negative. So if it's if not Q, then not P. So if you are not grounded, then you did not fail a class. Okay. Mm-hmm. That's it. Everybody good? Okay. All right, so let's look at these examples here. We've got this conditional that says, if the measure of angle A equals 95 degrees, then angle A is obtuse. Okay? So we're going to look at the truth value, and if it is false, you have to give a counterexample. It is possible that you could give an infinite number of counterexamples. You only have to have one. So sometimes every single one of us could have a different counterexample. And the counterexample is just an example of when it doesn't work. Right? It's what just kind of, ruins your argument there. So it says if the measure of angle A is equals 95 degrees, then angle A is obtuse. Is that a true or false statement? I only heard one true. I'm a little worried. True. Okay. It is true. Okay. So if it is true, there is no counterexample because it's true. So the converse. We reverse them and say, if angle A is obtuse, then the measure of angle A is 95 degrees. Is that true or false? False. Raise your hand if you want to give me a counterexample. Because if it's false, you got to be able to tell me why. Like, give me a counterexample. The counterexample is just the why is that not always true? Anybody? That the counterexample is the reason it doesn't work. The reason it is not always true. Elias, did you want to give me something? It could be more than 95 degrees. Okay, could it be, so you said more than 95, so could it be 583? No. Less than 180. Okay, so and that's fine to say it could be more than 95 as long as it's less than 180. You could just give me a number. What did you say, Sebastian? 91. Okay, so you could just give a number, or you could give a statement. Since we don't have very much room, we'll just use the number. So our counterexample could be that it could be measure of angle A equals 91 degrees. Because it just says A is obtuse. It could be 91. It could be 132. It could be a lot of things, right? Okay, Sebastian, sit up. All right, so then the inverse is when we take the original one and we make it negative. So if the measure of angle A does not equal 95 degrees, then angle A is not obtuse. So think about that one for a minute. If the measure of angle A is not equal to 95 degrees, then angle A is not obtuse. What do you think? True or false? False? Okay, why? Exactly. Okay, so you can use the same counterexample. Sometimes the same one will work more than once, and that'll work just fine. So that is false. And so the measure of angle A could equal 91 degrees. So then if angle A is not obtuse, then the measure of angle A is not 95 degrees. Does it get a little harder to think through? I mean, this is a pretty easy concept, right? But once you start throwing all the knots in and flipping it around, you start to confuse yourself, even on something easy, right? I've got a way I'm going to make that a little bit easier in just a minute. But what do you think about this one? True or false? True. True? Because if it's not obtuse, okay, if it's not obtuse, that means it cannot be between 90 and 180. So if I know for sure it's not between 90 and 180, then it's not 95 degrees. Does that make sense to you? So this is true. Okay. And then this gives you an example of, the symbolic form and then what you would actually say there. Now, I want you to look at, I don't think it shows up on yours as far as the shading is concerned, but it does on mine, that you see how these two are shaded the same and these two are shaded the same? Okay? Now, that's because the truth values match. You see that? And the truth values will always match on those. Now, listen carefully. That does not mean that every time you write something, it's true, false, false, true. Okay? Because it could be false, true, true, false. They could all be true. They could all be false. All right? But what has to happen is whatever the conditional is, whether it's true or false, the contrapositive is also. And same for the converse and inverse because they are related. So related conditional statements that have the same truth values are called, okay, and this is going to be some fancy sounding wording, logically equivalent statements. They are logically equivalent statements. This is way more important than you think it is, okay? This is what their whole argument was over in the calculus training, about which ones were logically equivalent and why it's important to know the truth values of all four and when they have to match and when they don't. And that's important to be able to relate all the rules that you have together when you're talking about theorems and some other stuff that you have going on. Okay, so it says, however, all four related conditionals can be true or false. So again, I just want to make sure that you know that it doesn't have to always be true, false, false, true, because there's always somebody that walks away with thinking that. Okay. Questions about that? One reason why it's false, even if there's an infinite amount of them. Okay. So this says, write a conditional statement from the Venn diagram. Right, so do we read from the inside out or from the outside in? Okay, let me ask you this. Think about what it says. If it's a tarantula, then it's a spider. Or if it's a spider, then it's a tarantula. Are all spiders tarantulas? No. Are all tarantulas spiders? Yes. Okay, now, here's what you can't do. You can't say, if it is a tarantula, because what the heck is it, right? Your English teachers do not allow that. That is not okay even when you're not in English class, because you have to say what it is, all right? So, what is a tarantula? No, because spider comes last. Okay, if an animal is, and it is an animal, tarantula, lives in the animal kingdom. You can go ask your biology teacher. Okay, if an animal is a tarantula, shut your mouth. Then it is a spider. Okay? If an animal is a tarantula, then it is a spider. Everybody good with that? So the inner oval, stop talking. The inner oval represents the P, the outer oval represents the Q. Okay, we good? All right, next page. So this says, write the converse, inverse, and contrapositive, and we're going to find the truth value of each one. So if two angles are supplementary, then they are a linear pair. Is that true or false? If two angles are supplementary, then they are a linear pair. What do you think? Okay, those of you that are saying false, you got a counterexample for me? I mean, you gotta have some reason you're saying false, right? It's whyever you think it's false. There you go. That's a fancy example right there. And if y'all weren't talking, you could have heard what he said. If two parallel lines are cut by a transversal, then same side interior angles are supplementary. Are same side interior angles a linear pair? Nope. So is this true or false? False. And you can say, we'll do two lines parallel, then same side interior angles are supplementary. Okay, everybody okay with that? Converse. We're going to switch them around, right? So when I do that, I can't start with if they are a linear pair. It doesn't work that way, right? So what are they? Two angles. So if two angles are a linear pair, then, now I can say they are supplementary. Okay. So what do you think about that? True or false? True. Because if they're a linear pair, they are supplementary. That is part of the definition, right? So that is true, which means I don't need a counterexample. So the inverse. For the inverse, which one do I make negative? The conditional or the converse? The conditional, right? So I would say if two angles, what? Are not. If two angles are not supplementary, then they are a linear pair. Oh, then they are not a linear pair. Sorry about that. Okay, I'm teaching, sweetheart. Okay, so then they are not a linear pair. Okay. So is that true or false? Do you even have to really read the statement? No, because these are logically equivalent statements, right? Yeah? Okay. So we're going to have to finish this tomorrow, and because I want to talk through some of this, I am going to go ahead and give you the homework, though,